Hello, class. Today we're going to discuss magnetism. The first definition you're going to learn is that magnetic fields are produced by moving charges or moving electrons. One concept to learn is that a magnet has a north and south pole. Like poles repel and opposite poles attract. A second concept to learn is that if you break a magnet in two, you get two new magnets with its own north and south pole. Ferromagnetics are types of metals that can be magnetized. Microscopically, atoms are made up of microscopically, atoms that make up ferromagnetics are in a random order. Now remember, all atoms have electrons buzzing around them constantly. This figure below groups chunks of atoms into domains. When these domains or atoms are randomly organized, no magnetic field is produced. But if you were to magnetize this piece of metal by bringing an external magnet close by, the domains or atoms will line up. If the atoms are lined up, the electrons start flowing in the same direction. Now remember the first definition, magnetic fields are produced by moving charges. So the aligned domains or atoms work together to produce a magnetic bar. A magnet, if undisturbed, will tend to retain its magnetism. It can be demagnetized by shock or heat. The relationship between the external magnetic field and the internal magnetic field in a ferromagnetic is not simple, as magnetism can vary, and we won't go into detail on that. The figure to the left uses iron fillings to help you visually see the magnetic field lines. The figure to the right is an artistic way of showing the magnetic fields by using lines, because in real life the magnetic field is invisible. A couple of things to know about magnetic fields. One is that they always form in closed loops, and second is that charged particles will move around the magnetic field lines, not along. And then lastly, magnetic field lines come out of the north and into the south pole. Our Earth has a magnetic field surrounding the whole planet and protecting us from the solar storms produced by the sun. A simplified version of the Earth's magnetic field lines is similar to a barb magnet. Note that our so-called magnetic north pole is not aligned with the Earth's rotational axis, and its location moves over time. Also note that the Earth's north pole is really the south magnetic pole, as the north end of the magnets are attracted to it. Here are two opposite poles facing each other. Note that the magnetic field lines are nearly uniform, out of the north and into the south. There are three right-hand rules that I'm going to teach you. Right now, I will say that this is right-hand rule number 1. But first, let's take a look at a wire with current flowing through it. Remember how magnetic fields are produced? Correct, moving charges or moving electrons. Well, guess what? Charges are moving through the wire and produces a magnetic field around the wire in closed loops. The right-hand rule, number 1, states that if you point your thumb in the direction of the current, your fingers curl in the direction of the magnetic field lines, as seen in figure D. If you have current flowing in a loop, you can still use the right-hand rule to determine the direction of the magnetic field lines. Take your thumb, point it along the direction of the current at one point on the current loop, and your fingers point in the direction of the magnetic field lines. In the example to the far left, the fingers point in the inside of the loop towards the right, and the circle on top of the hoop points towards the left for the magnetic field lines on top. The middle figure shows an example of what magnetic field lines look like around an object with current flowing in a loop. The magnetic field lines are represented in green and kind of have a donut shape if it were in 3D. The last figure to your right shows what the magnetic field lines look like around a coil. Does the shape of the magnetic field lines look like something you've seen before? That's right, a bar magnet. A coil and bar magnet have the same shape for magnetic field lines. You can tell which end is north because the field lines come out of the north and into the south. Now we're going to learn the second right-hand rule. In this example, we have a wire with current flowing through it, and it's placed in the present of a magnetic field. In this case, the wire is placed in between a horseshoe magnet. The right-hand rule number 2 states that if your arm is pointed in the direction of the current produced in the wire, and your finger is curling in the direction of the external magnetic field lines, your thumb will point in the direction of the force. That's right, I said force. The wire will physically move if placed in an external magnetic field. The example to the left has a wire forced downwards, and the example to the right has a wire forced upward. Notice that all 3 of these vectors are 90 degrees from each other. Here's an equation to calculate the force on a wire when placed in an external magnetic field. F stands for magnetic force, I stands for current, L stands for the length of the wire in the magnetic field, and B is the variable we'll use for magnetic field strength, or often just referred to as magnetic field. Theta is the angle between the direction of the current and magnetic field. Often, theta is 90 degrees. Now, please take note of the close wording between magnetic force and magnetic field. Magnetic force is variable F, and magnetic field is variable B. The unit for magnetic field is Tesla, using the letter capital T. We will not use Gauss in this course. Okay, so for our first example, we have a wire carrying a steady DC current of 30 amps that has a length of 12 centimeters between poles face of a magnet. The wire is at an angle of 60 degrees to the field. The magnetic field is approximately uniform at 0.9 Tesla. We ignore the field beyond the pole pieces. We want to determine the magnitude and direction of the force on the wire. We'll start with our new equation. From there, it's just a straight plug and chug to calculate the magnetic force on the wire. So we plug and chug to get 2.8 newtons. Oops, I forgot to mention that the direction of the force is into the page. That's the direction that the thumb is pointing. In exercise D, we have a straight power line that carries 30 amps and is perpendicular to the Earth's magnetic field of 0.5 times 10 to the negative 4 Tesla. What is the magnitude force exerted on the 100-meter line or the 100-meter of this power line? Well, we'll start with the same equation. Plug and chug to get 0.15 newtons. So even power lines feel a force due to the Earth's magnetic field.